Hello folks, this is Dan Watson, Certified Lubrication Specialist and longtime AMSOIL dealer. I'm here with another edition of the Lube Page. This Lube Page is brought to you by thelubepage.com, Dan Watson, and AMSOIL Synthetics. Now, I've started these videos again, many of you that have followed me over the years, because I was sort of in retirement and then I decided, you know what, I get so many questions over the same things over and over that I think I'll just come back on the YouTube videos, explain a lot of things, and my goal is to give you the tools to make your own decisions and to understand enough about these lubricating products that you'll come out with an educated decision, because in the end, you're the one that bears the responsibility for the maintenance and the life of your vehicle, your snowmobile, your water ski, whatever it is that you have. You're the one that's going to take care of it. Everybody else is willing to give you something to take care of it, but in the end, you're the one that makes the decisions on exactly what the best product is going to be. So I'm going to start out with some fundamentals over the next couple of videos that we're going to do, so that if you don't understand these fundamental issues, then it's hard to discuss the applied principles of these lubricants when you put them into an application, because you have to use terminology and you have to use technology that if you don't understand it, you don't understand what I'm saying. It's like I'm speaking Greek and you're fluent in French. It just doesn't work. You have to understand these principles. Okay, so I'm going to start out with the number one priority characteristic of a lubricant, lubricating oil, a liquid, and this is the term called viscosity. Say it again, viscosity. All right, now we have a lot of slang ways that people talk about what we call viscosity. They say, well, what's the weight of that oil? Is that a heavy oil? Is that a light oil? Those are different terms that have some validity in them. But the true thing that we are trying to understand about that lubricant or that liquid is its viscosity. So we need to know what that means. What exactly is viscosity? Now, the easiest way to look at viscosity is to just simply say it's whatever is the resistance of flow of the liquid at hand that we're looking at. And that means flow makes sense to anybody. Flow is that it's actually flowing, it's moving, okay? Now, the resistance to that means it's not going to move very easy. So viscosity is measuring the resistance, or which is actually the inverse of the flowability, which is another term some guys use. So how do we look at that? Well, age-old examples. Water has a very low viscosity. Molasses has a high viscosity. So that's pretty easy to understand. This stuff over here, it moves like, you know, snail pace. When you try to pour it, it flows very, very slowly. And the other product, the water, it moves rapidly, pours right out. If you had a beaker full of each and you started to pour them out, before the molasses could get the first couple of globs out, the water-filled beaker would be empty. So viscosity is a measure of the resistance to flow, not the flow, but the resistance to flow. So that means that the viscosity of molasses is very high, the viscosity of water is low. All right, now back to some of the terms that people use, because I don't want to discount them completely. I would agree that you could look at it and say that a highly viscous, I can say that, a highly viscous fluid would be thick. That's a pretty good observation. And a low viscosity would be thin. So those observations and using those terms doesn't mean it's completely wrong, but it's not actually the official definition, if you will, of viscosity. And we also have the term that's used a lot of times, well, you got to use a heavyweight oil or a lightweight oil. Now, to understand that is that most of the time when we're dealing with oil, if I have a high viscosity oil, it will actually weigh more than the low viscosity oil. Okay, so that's where that kind of comes from. Back in the I call them old days. I hate to say that old days because that would date me. But back in the beginning, when you sold these products, they would sell it by the ton or by the hundredweight. And so if I had a very thick, viscous oil, it would weigh more. So, hey, I got to get that heavier oil, okay? And that was a way of looking at it. So I'm not discounting that completely either. But remember, we need to be able to understand this term viscosity, because in future videos that I hope to produce, we're going to be talking about the characteristics of oils and how they function, how they lubricate, and we need to always know when we're using the term viscosity what we're talking about, so that we can understand those applications and how the oil will perform in different circumstances. Now, going deeper into why viscosity is important in the world of lubrication is that any worthwhile lubrication engineer, and there are those people with that title, there's only a couple of universities that still graduate what's called a lubrication engineer, but they're there, will tell you that the single most important aspect or characteristic of a lubricating oil is the viscosity, because different applications of lubrication require different viscosities of oil. Just quickly, an example would be that if I have ball bearings or roller bearings, light viscosity, low viscosity numbers for roller bearings or ball bearings. But if I move up to a large shaft, for example, like you might have in a propulsion system in a ship, big shaft going back, I'll have a thicker oil because I'm trying to ride that shaft on a wedge of oil, and it'll be thicker for that application. So different lubricating regimes or applications require a different viscosity of oil. So you start out as a lubrication engineer when you're going to determine the correct lubricating product for an application with, well, what are we going to need for the viscosity to get the proper protection in this application? So that's why, again, we come back to viscosity, but it is extremely important in the world of lubrication. Now, one thing about viscosity to understand is that when we get this term thicker or thinner, it actually relates to what would be the film of oil. What do I mean by that? Well, if I take a piece of metal and I just pour enough oil to cover the surface, let it sit till it covers the whole surface, and then I go, well, how thick is it? Meaning, what's the millimeters of thickness of that oil film sitting on that metal surface? Now that's oil film, and the thickness of it is important, because the thicker the oil film sitting on the surface of the metal, the better that metal can keep two metallic surfaces separated. Hence, that's the whole world of lubrication. I've got metallic objects, and my goal is to make sure they never touch each other. You'd say, well, that's pretty easy. You could have a real thin film of oil. Those smooth surfaces, believe me, they're not smooth. If you take even a 4x microscope or magnifying glass and you look at the surface of a piece of machined metal, it will have, it looks like, magnified like a little mountain range down there at the subvisible level, because it's got all these little peaks and valleys. They're called asperities. And what we have to do is make sure that our film is thick enough that those peaks never hit each other as these guys are going by. Because if they do, that's called wear, and we're starting to take metal off the surfaces. So the thickness of the oil film is important to keep the two metallic objects separated, and that's directly proportional to the viscosity, So we need to know where we're putting it, how smooth the surfaces are, and how thick of an oil we need to keep it separated. So again, here comes viscosity. It's very important in that application. And that brings us back to really why I'm doing this different than you getting a science lecture on some other part of the web, is that this has all got to do with making this applied to lubrication. And why do we even lubricate? It is to reduce friction and prevent wear. That's why we're lubricating these surfaces, okay? So that comes back to why this viscosity is so important, is because we got to keep those metallic objects separated. Now, later on, I'll talk to you about additives of zinc and phosphorus that are put in that we'll deal with sometimes when we lose the ability to have a complete oil film separation. But that's not part of this lecture, but that's another important part. So, this viscosity is important, so the question is, how do I measure it? How do I know what does the viscosity level of 12 versus the viscosity level of 24, what does that mean? How did I measure that, and what's that scale that I'm talking about? So we have to come up with a method. Now, one clear thing to note is that there's an organization called the American Society for Testing of Materials, okay, ASTM. The ASTM is the authority on testing methods, okay? If it's not an ASTM test, then don't pay any attention to it. It may have some relative information, but it's not a repeatable test that can be done by any individual and come up with the same results. If a test is oriented in such a way that it depends upon how the operator of the test does it, then it's a biased test, and it's not recognized by the ASTM as being a actual certification test. So that's just a side note to be important to understand. So they developed tests for viscosity. There's two types of viscosity. There's a kinematic viscosity and a dynamic viscosity, or dynamic is sometimes called absolute. Kinematic is sometimes called movable, okay, or motion. Now here's real simple. Kinematic is what we deal with mostly. We're worried about, that's the numbers we get in lubrication. There is a place, I'll tell you about it in just a minute, where the kinematic viscosity, there's a substitute for it. But kinematic viscosity applies to those numbers that you see on the oil bottle that we talked about in my last video, where it says 5W30. Those numbers, the 30 side, is kinematic viscosity. Well, what does kinematic viscosity mean? Kinematic means it's associated with motion. Well, we're interested in that because we're talking about viscosity, which has to do with motion, right? So how do they do it? Without having a diagram to show you, it's really simple. I take a volume of oil in some type of beaker or glass container. I make sure that that oil is at the exact temperature, and I know what it is because I put it in, it's in boiling water to where it will be 212 degrees, because when water reaches 212 degrees, it makes steam, but the water stays at 212 degrees. Okay, now, what happens is I've got this oil volume sitting here. Well, I have a glass tube that goes down, and it has an actual restrictor or orifice in it, and the idea is to see how long, and measure how many seconds it takes for this liter or 100 milliliters, whatever it is in the particular test, to drain through that down to another collection device. They measure those and the number of seconds it takes. In the old days, it was called Sabot seconds. Okay? That's still used internationally, but it's really not the current thing. The current thing is we take that information, we put it on a scale that's called centistokes. Centa means 100 stokes, okay? And this has all got to do with further measurements that we don't need to get into. But what it tells us is that if that goes down in so many seconds, we're able to put that on a scale and we say, well, that's a 14 centistoke oil, because it took so many seconds to go down through that kinematic viscosity. Okay, so that's how we measure kinematic viscosity. We want to see how fast it flows, and that's important because this whole thing about viscosity is to try and understand how this liquid flows. Okay, that's what viscosity is telling us. Does it flow easy? Does it flow slow? Well, by measuring the seconds it takes and working out a scale that I can convert this to, now I've got a method to say, well, you know what? A 24 viscosity, 24 centistoke viscosity, it flows less easily than a 12 centistoke viscosity. Because why? Because the viscosity at 24 is actually higher than the viscosity at 12, and we know from our previous discussion that it's going to have more resistance to flow at 24 than it is at 12. So we've devised a method to test it and to have a scale that we can test different liquids on and determine their viscosity measured with units called stokes, and in this case centistokes. Okay, now that's good. That's what we use, but there comes a point that we need to know something a little different than just how it flows. We need to understand the internal resistance to movement. Now that's what dynamic or absolute viscosity really is. It's measuring the resistance to changing your form as a liquid. In other words, for a liquid to flow, it actually has to change its form, make a stream, and head off and flow. But if it just sits there like pudding and doesn't move, then we would say that the absolute viscosity of that is very high, maybe 600 or something, okay? So we're going to do this a little different, and we're going to end up with a different type of unit. Instead of centistokes, we call it centipoise. Okay, we're not going to get into the derivation of how you get the centipoise versus centistoke, but just remember, it's got a different unit. Okay, why is it important to us? Well, think about this for a minute. If I have a gear set sitting in a volume of oil and it's cold outside, I want to know how that liquid is going to respond as those gears start to move inside that liquid. How much resistance will it actually change its form and flow over the gears? Because in very cold situations with some standard petroleum lubricants in a gear set, you'll get what's called knifing or cutting, and the gear will just cut out a section and be spinning, and there'll be no oil on it because it will have pushed the oil to the side and cut a groove in it, because there's a very high resistance to changing shape internally in that liquid. That's dynamic or absolute viscosity. Now, why do I care about that? Well, I just explained it. We do have gears and we have other things that we put in a volume of oil, and we're trying to lubricate them, and they may be in extreme cold conditions. So how are we going to make sure that this oil is going to move and change its characteristic or change its shape in order to get around those gears and do the job? So we come out with a test that would better test this than the kinematic or the movement flow coming down through from a beaker. And this test is where we take a little round glass beaker, and we put a magnetic device in here, and the little motor underneath has a magnet in it. It's called a magnetic stir over in the chemistry lab. But what we end up doing is we have this little motor, and we have a precision amp meter. This is how many amps does it take to turn that little motor. Well, when that motor turns, that locked-in magnet inside that volume of oil in this beaker, it's going to turn with it. But boy, that little motor is going to have to put some effort in to turn it. That's registered by the amps that's being pulled in order to turn the motor. Okay, now that we've got this and we figured it out, we can take different viscosity oils, and we can do this test on them, and we can determine at what amperage we see a certain activity that takes place, make a scale called centipoise, and now we know what the centipoise reading would be for, quote, what, a 5W. See, that's what that W really is for. It means that this oil is not tested. That 5W doesn't mean it was tested with kinematic viscosity. It was tested with this absolute viscosity device to determine how easily a object can rotate in that volume of oil. It's important because that's what's very important to us on the cold side of lubrication. So, okay, we've described two ways to test it and two types of viscosity. But that's important because, see, we just brought it right back to, well, that's where you get your W ratings. They're tested with this little device to rotate the magnet inside this magnetic stir to get an amperage reading and to convert that over into a scale for centipoise. That's completely different. So when somebody says, well, that's a 5-weight oil and a 30-weight oil, no, it's not. It is a 5 winter rated, and it is a 30 viscosity for operational viscosity. This one's done, the 30 is done on a kinematic test, and the W one is done on absolute viscosity or dynamic to check the internal resistance to movement. Okay, so we beat that to death. That's enough to understand that. Next thing, what happens to these liquids if they get very cold or very hot? Well, remember, this is a liquid, and just as much as everybody understands water, what happens when water gets really hot? Turns to steam. What happens to water when it gets really cold? Becomes solid and goes to ice. What that's relating to, it's called phase transformation. I changed from a phase being liquid to being steam. I changed from a phase of being liquid to being ice. Phase transformation, very important concept. Now, when I look at it in lubricating oils, we talk about a pour point and a flash point. Pretty easy, almost intuitively easy to understand those. The pour point is the temperature at which really it will no longer flow, or you could say the first temperature measurement that it will actually flow out of a beaker. That's called the pour point. Why is that important? It doesn't matter about all of our viscosity measurements and everything else. If the oil has reached this phase transformation point where it's becoming almost functioning like a solid, it's all the throw out the window anything to do with flow or anything else. The oil's now gone into phase transformations, become nearly a solid. Top end, what kind of viscosity do I rate oil vapor? There's no viscosity to oil vapor. It's vapor. It's gone. I've lost all my characteristics of that. That's why we're so concerned in high temperature situations. If we get oil up and it starts to vaporize or flash off and lose its viscosity, then what are we going to have? Nothing to separate those moving metallic parts. We're going to have big wear, big problems. So we don't want that. Okay, so pour point and flash point. Just straightforward, easy to understand. Now, the next part I want to talk to you about, it's called viscosity index. This is very important in lubrication. So, drop your pencil or whatever and take a look at me and make sure you get this, because viscosity index is a measure of how much the liquid will change its viscosity with respect to temperature. For example, just pick some numbers out of the air. If I had a lubricating oil that was viscosity 10, and it turned out that if I went up from where it's measured 10 at 212 degrees, let's say, that's measured there. If I went to 250 and that oil went from a measurement of 10 down to 5, that'd be pretty severe loss of viscosity due to increased temperature, and that would mean that it had a very poor viscosity index. The higher the viscosity index, the less the liquid will change with respect to temperature. Now that's important, and in our future discussions about engine oil and transmission oil and all these kind of things, viscosity index is going to become an important characteristic, because we need to know what happens when these engines get really hot or they get into a strained situation and the temperature goes up out of the normal operating band. Are we going to lose all of our viscosity and seize the engine or burn it up, or what are we going to do? And by knowing the viscosity index rating of the oil, it'll give us a better idea of how well we're going to be able to handle either high or low temperatures. Do we want the oil to start freezing really bad at minus 15 degrees? It starts freezing? Or would we prefer that our viscosity index said, well, wait a minute, this oil doesn't change much with regard to change in temperature, so you're going to have to get a whole lot lower in temperature before it begins to freeze and reaches its pour point? Okay, so viscosity index, important concept. It's going to come up over and over. And there's one that I didn't even have written down here that I want to tell you real quick on. When we measure in oil, talking about viscosity, we get into high performance situations. We have a measurement called high temperature, high shear, and what that means is that we force the oil to a temperature of about 300 degrees Fahrenheit, and we kick up to an 1800 RPM situation, and then we have a test which will tell us how much viscosity remains on that rotating member. And that's the high temperature, high shear rating. And I guarantee you that if you have a turbocharged vehicle, either diesel or gas, and if you have a high performance, you got yourself one of these really great high performance cars, that number is critical to you, because you're going to push that engine into situations where that high temperature, high shear tells you whether you've got liquid protection left or whether you've moved into another situation, which we're going to talk about in another video. So this is viscosity, and I'm just going to bang right down rather quickly to give you a quick review of what we've talked about. We defined viscosity, the resistance to flow. We talked about why it's important, because we got to keep those moving pieces, those moving metallic objects separated by a film of oil, and that film of oil is directly related to the viscosity. Okay. Then we talked about how we measured viscosity, and we said that you have to use the ASTM testing for it to have any validity. And we talked about kinematic viscosity and how that's tested, and flowing from one beaker down to another and timing it for the seconds it takes. But that has to be at 212 degrees at atmospheric pressure. Okay, so those things change, as you know, if we change the temperature and we change the pressure. If we're testing it in Denver versus testing it in Orlando, Florida, we would get a different test. So to test those things correctly, you have to have correction factors for if you're not at standard temperature and pressure for that test. We talked about the difference between kinematic and dynamic or absolute viscosity. We went on to talk about pour point and how that's hey, you reach a certain coldness, it no longer pour out of the beaker. We talked about the flash point, which is you get up to a certain temperature, it makes vapor. It's no longer responding within the characteristics of a liquid. We went on to talk about viscosity index, very important, and that again is related to how quick or how fast or how much does this liquid change with a change in temperature. And we want it to be stable. We don't want it changing rapidly or high rates due to temperature. And the natural, they call them Newtonian fluids, will change just like a linear line. The viscosity will change with the change in temperature. Now, when we make these multigrade oils, these 5W30, 10W30, 5W40, those things, which I'm going to talk more about how those are made and how they put them together, they will be very dependent upon the viscosity index to try to stabilize them and the way that they're put together, because they're no longer functioning as a Newtonian fluid. Newtonian fluid has a direct, easy to understand relationship that's linear to the change in temperature, but non-Newtonian fluids like multi-weight oils, they do not have those characteristics. So we'll talk about those in the future. So again, it's great to be back. I hope you get something out of these videos. You can hit the like button at the bottom of the video, and that'll make sure maybe some other people get a chance to look at it. And as always, I'm in business myself in the lubricating business, and I'm not bashful to ask for your business. I am a certified lubrication specialist, and I am an AMSOIL distributor. So if you're looking for synthetic oil or you have questions on applications, then you can call me at 800-370-2986, or you can go to my website, which is up behind me here and which is on the screen for you, and you can contact me via that application. So I'm easy to get in touch with, and again, I'd certainly be happy to have your business if you want to support me in what I'm doing. So until next time, this is Dan Watson signing off.